Okay, I'm going to try and give a pre-recorded lecture for this class to replace the recording that didn't work on last Tuesday. So the things that I want to cover are angular momentum for a rigid body, but including the center of mass motion and spin. And then we had a couple of examples. So things like with a string with a spool and a mass connected to a spool, how did the mass accelerate? So we'll do that example too. So the topic we're going to talk about is angular momentum again. And so on this lecture, before I had done this lecture, we talked about angular momentum for a point. And so now what I want to do is define angular momentum or for a rigid body, so integrating up the mass in an extended object. So remember, L was R cross P, and P is mv, so this is R cross mv. And this was true for a point mass. And so now we want to find the total angular momentum of some rigid body. We want to integrate this up. So so now instead of having just a single mass for a point particle, it will be L cross dm. So integrating up overall masses, and then V. And of course, these are both the velocity and the position from some origin are going to depend upon where, where this little mass cube is. So, if I have a body like this, I have some little cube of mass dm, and it's moving at some velocity v, and it's some radius from an origin. So we have to specify the origin in order to do the integral. So, so this is what we're going to integrate up to get the total angular momentum of an extended but rigid body. And yeah, so to do this, it actually helps to work with a couple different coordinate systems. So I'm going to define 3 different coordinate systems. So 3 coordinates systems, actually. And this is pretty typical of any spin dynamics problem that you have more than one coordinate system to work with. So I'll just give this an example of that. So the first coordinate system will be an inertial coordinate system. So like this one. So we have the inertial one, inertial. And so let's call that one X. So this is going to be X, Y, and Z. Then we have, so inertial would be, a background, not moving, not spinning coordinate system. Now we'll subtract off the center of mass of our rigid body. So we have a non-spinning center of mass coordinate system. So I'm going to call that X prime. This X prime, Y prime, Z prime. And then the last coordinate system we're going to have with respect to the body itself. So I drew kind of a blob here, but think of the Earth, and we have latitude. This is the North Pole and the South Pole. So this direction you specify latitude, and this direction you specify longitude. So every point on the Earth has this particular coordinate, and the Earth is still spinning, and so those coordinates move with the spinning Earth. And so we're going to have a spinning coordinate system. Coordinates, but they don't move on the body, or they stay with the body. So they stay with the rotating body. Stay with the body. And this is also with respect to the center of mass. And so I'm going to call this xi, y, zi. So I is like internal, like for the body itself, because like so latitude and longitude on the Earth are coordinates on a surface, but you know, we could also put it in depth, for example, there, and then we would get all the little mass elements inside the Earth. Okay, so those are our 3 coordinate systems. Yeah, so definitely useful to have more than one coordinate system when you do spin dynamics. So now that we've defined our coordinate system, I have to relate them to each other. So let's write again what they are. So we have x, I'm going to call that inertial. Then we have x prime, that's the center of mass. And then we have xi, and that's the body one. It's also a center of mass. So this one's rotating and not rotating. So let's just remind ourselves. Okay, so let's relate these two together. And in order to, like for example, so in order to go from the body coordinate system to one that's not spinning, we have to rotate the body. So an example is, again, longitude and latitude and longitude on the Earth, but then what position is that? Is a point on the Earth's surface with respect to the background stars? Yeah, so that's exactly what we want to do here. So we need to rotate this coordinate system to get that one. So I'll define a rotation matrix. So to make this problem a little bit easier, I'm just going to rotate around the z-axis only. So just to show how you do this, and you could do this in any direction, but it's a lot easier with a single rotation. So we have a rotation matrix. So if I'm rotating around the z-axis, I'm only rotating in the xy plane. Only depends on the rotation angle. So that a rotation matrix looks like this. 1 and then zeros like this. And then I have a sine theta. And depending upon which way you want to rotate, either this one's minus or that one. And so let me show you more exactly what this looks like. So x, that's this coordinate system prime, is going to be the rotation matrix times the body coordinate system. And so I can write that out like this. Put the rotation matrix in. Minus sine theta 0, 0, 0, 0. I have x, I, y, I, the internal body coordinate system. And now I just multiply this out if you want to know what x prime, y prime, and z prime are. So this is cosine xi cosine theta minus yi sine theta. And then we have sine theta cosine xi sine theta plus yi cosine theta. Right, and then this one, I have 0, 0, 1, so z doesn't change, okay? So that's how we go from the body coordinate system to the center of mass, but not rotating coordinate system. And now what if the center of mass is moving? All I need to do now is to get the inertial coordinate system is add the center of mass in. So the coordinate in the inertial frame will be the center of mass position plus x prime. Like that. Yeah, okay, so I could write this out. So if I wanted to, yeah, so let's do that. Yeah, I'll just write this out. Just put down here x, y, z is going to be x center mass, y center mass, z center mass, plus this thing, xi cosine theta minus yi sine theta, xi sine theta plus y cosine theta zi. Okay, and that's our coordinate system. So so let's leave this here. And we in order to calculate angular momentum, it's r cross v. So we've got r, but this is now r. That's actually the position in the inertial coordinate system. But we need to know v, and so we need to take a time derivative of this. And so the center of mass could be moving, so this will turn into the velocity of the center of mass. But then it could be rotating, so theta could be d theta dt will be an angular rotation rate. So we can take the time derivative of this to get the velocity in the inertial frame. So let's do that. I'll just leave this here. So Vx, Vy, Vz, and this is in the inertial coordinate frame, will be V center mass X, V center mass Y, V center mass of Z. It's a vector. Now I need to take the time derivative of this thing. So xi is in the body frame, and we're assuming it's a rigid body, so the points in the body are not moving. So this is time independent. Cosine goes to minus sine. And then we should take the derivative of theta dot. And now we have minus yi. Sine goes to cosine when I take the derivative times theta dot. This doesn't have anything. So I have xi, sine goes to cosine, theta dot, minus, so minus yi sine theta dot. So you notice everything here is multiplied by theta dot, so I can take the theta dot out. Okay, so that's good. So it's actually useful to notice. So this is, did I do this all right? Yeah, it looks okay. So notice this is xi cosine theta, and this is yi sine theta. So those are the same thing. So I can also write this. This is x is equal to v center mass plus this turns out to be minus that, and that's y prime. And this is the same as that, so that's x prime. So it's just useful to do that. Oh, and we have this time derivative of that. So using theta dot is equal to omega, or angular rotation rate, we can write v as the center of mass velocity plus this vector times the angular rotation rate. Okay, good. So so we have x or r, and we have v, and that's everything we need now to specify a point inside our rotating body. And so now what we're going to do is integrate this up over the body and see what we get. So so let's write out the total angular momentum. So let's write out the angular momentum just for one little mass element. And so I'm going to use Lx to be the angular momentum of just one particular position. So it's and this is going to be per unit mass, so I'll multiply the mass later. So let's take x across v. So this is just for one little mass element at the position x. So here's x, and here's v. So I need to do this across that. So it will look like x center mass cross v center. Well, let's just write each one out, and then I'll distribute the cross products, and so it's x prime because this is x prime. That's right. Now we have v center mass plus this thing minus, so I'll just write it horizontally, minus y x prime 0 times omega. There. So that's equal to the angular momentum per unit mass particular coordinate. So now let's write this out. So it's x center mass cross v center mass plus these are all vectors, and we have x cross v center mass like that, plus x times this thing, so it's x center mass times y prime x prime 0 omega, and then the last term, which is x prime cross minus y prime x prime 0 omega. Okay, so that's each term. And now to get the total angular momentum, I need to integrate up this Lx over the mass distribution. So that's going to be x center mass times v center mass over dv times rho, actually. So this, and then we'll get terms for these ones. So let's write those out. Right, so this will be the integral of x prime rho dv times cross v center mass. So I'm going to move this to the side because this doesn't depend on where you are inside the body. And then we have plus x center mass times the integral of these things, y prime x prime 0 rho dv, like that, times omega. And then the last term is the interesting one, is this one. And if you multiply this one out, I'll multiply it out, what we get is this. So because this is x prime, y prime, z prime, so you have to take the cross product there. It winds up looking like this, x prime, z prime, y prime, z prime. Yep, and an x squared plus y squared primes times omega times rho dv. Okay, good. So, so this term, these are not dependent upon where you are in the body. So all we could move the integral here to just be over the body. And when we integrate the mass distribution over the body, this is just the mass, total mass. So I can replace this with the total mass. Yeah. So this, if you look at this is x integrated over the mass, but we specified that this x prime coordinate system is with respect to the center of mass. So if we integrate up x times rho, then we'll get 0 because that's the center of mass position. So this is going to be 0. And this part goes away for the same reason, actually, because this is y integrated over the mass distribution, so this is 0. And that's x over the mass distribution. And here we can do the x prime integral first. And so integral of x over the mass distribution is 0. So this thing is going to go to 0, and that thing's going to go to 0. So this is not going to go to 0, but that's the distance from the center of mass. It's actually the distance to the rotation axis. And so the integral of rho times r squared, which is the distance to the rotation axis, is actually the moment of inertia about that particular rotation axis around the z-axis going through the center of mass. So this thing is actually I omega. So that's what it is. So where's because we have an omega there. So let's get rid of these terms because they go away, plus I omega. And so what did I show here? What I've shown is that you can take a whole rigid body and write the angular momentum as a translational bit plus a spin. And the translational bit is just the angular momentum of the center of mass. So it's m x, the position of the center of mass, cross the velocity of the center of mass. And the spin is the moment of inertia times the angular rotation rate. And this has a direction, so this clearly has a direction. So we associate the direction of the spin with the rotation axis. And then that gives us the right, actually I removed it, but it was in the z direction, actually, the z hat direction, so I shouldn't have erased it so quickly. We did have the directional information there. Yes. So this you can think about how this kind of shows you how you can take problems and say I describe the angular momentum as the or in celestial mechanics we describe it as orbital angular momentum and spin angular momentum separately. So one of them has to do with the spin of the planet, the other one has to do with the orbit of the planet around the sun. And you can decompose the total angular momentum often into these two specific quantities. So yeah, so the basic thing is L is I omega, and that's the thing that you kind of have to remember. So that we did this with angular rotation around the z-axis. Well, what if we had, angular rotation around some other direction? For most of the problems in this class, we'll stick with a single direction that things are allowed to rotate. But so you need to this is a vector because it could be in any direction. So I need to multiply a vector by something that gives me another vector. And so a more general way to talk about this, so you turn this into a matrix, or actually one would call it a tensor. So what's a tensor? It's really just a matrix in this particular setting, but it rotates. So you can rotate it. So I is often called, when we worry about a rotation spin in any direction, like precession or something like that, we talk about the moment of inertia matrix. And then matrix times vector will give you vector. So you'll learn about that more in the classical mechanics class and in physics 235 next year or the year after, depending upon when you take it. Okay, so that's the angular momentum of a rigid body, basically. So that's what I wanted to talk about. Good. So let's give the example that I gave at for the same lecture. I guess did I go talk about torque in this lecture? I think I did. So we need to talk about torque. Before I give this example, we need to now be a little bit more careful about what's torque. Okay, so let's define torque. So the next thing to do is motivate, what do we mean by torque? So that's angular momentum for a rigid body. Torque, what's torque? Torque. So the analogy for torque is force, really. So when you have momentum and you find out how fast it changes, that's force, right? So if we have angular momentum and we want to know how fast does angular momentum change, that's torque. So let's so we could start by defining it, R cross F, actually, and it's going to be dl dt. So right, so let's show that these are consistent. And so if I take L, which is R cross P, then I want to take the time derivative of both sides, right? So dl dt is dr dt cross P vectors plus, so I'm just going to use the chain rule here, R cross dp dt. Okay, so dRdt is actually v. So this is v cross p plus r cross dp dt. So p is always in the same direction as v. So in the classical setting, p is mv. So since these are in the same direction, the cross product is 0. And dp dt is equal to f. And so this is equal to r cross f. Okay. So why is this? So when we take, and torque is defined as dl dt equals r cross f. So this is torque. So you don't have, yeah, so it's, so what is actually torque? Torque is kind of like, you take a force and you apply it across some lever arm angle. So often you're thinking about, when you talk about a torque wrench, you're talking about you take something, you put it on a bolt, and then you put a big lever arm on it, and then you push that way. And so that's like, it's giving a force perpendicular to the lever arm. And that gives you an R cross F term, which then exerts a lot of force trying to turn the bolt. So that's what torque is. So qualitatively, when we think about a rigid body, so if I have a rigid body, and it's, let's think about positions with respect to some coordinate. If I exert a force on this, then what happens to the component of force that's along this radial direction? Well, if it's a rigid body, then I can't change the length between these 2 points. And so the force doesn't do anything. It can't move anything. And so the only important part of the force is the component that's perpendicular to this vector. And that's what R cross F essentially does, is it removes the component of the force. So this is force, and this is the radius inside the rigid body. It gets rid of the part of the force that's parallel to the vector from the center of the body. And so that's the part that then when you're allowing the body to now turn, so if this is like the pivot point, then that force goes into the angular acceleration of the body. So that's qualitatively why you get this cross product in the definition of torque for rigid bodies. Okay, so now let's go back to our definition for spin angular momentum. So we had spin angular momentum is I omega, where this is now a vector that's oriented along the rotation axis. So, if I have a wheel or something and it's spinning this way, omega is in that direction. Spin. By the way, this is using the right-hand rule, so it's spinning like that. So what does it mean to take, so I want to take the time derivative of this now to get the torque. So supposing I is not going to change, then I have this vector omega. So if I apply the torque along the direction, so if this is omega, then, and assuming we've got some symmetry here, like it's a spinning disk or a sphere or something like that, then the angular momentum is in the same direction. So that's not always true, but let's just take that, give this object enough symmetry so that this is true. Then if I exert a torque on the same direction, then I'm just going to increase the angular momentum, but not so DL is not, so if torque, So if torque is dl dt is parallel to L, like they're in the same direction, then I'm only increasing L. So dl would be in the same direction of L. And if I is the same, that means omega doesn't change direction. So in that particular case, torque is I omega dot, but in the same direction as omega. So remember, omega is d theta dt, so this is going to be alpha in the same direction, where alpha is omega dot is d squared theta dt squared. So this is angular acceleration. So if I have a spinning thing and I exert a torque in the same direction as the spin, that's like taking a wheel and just kind of making it spin faster. I'll speed it up. It's you know, kind of what you expect. But what if I exert a torque in this direction? So if I exert a torque in this direction, then the change in angular momentum is not in the dl would be in this direction. So what that does is change the axis of rotation. So you have to kind of figure out when you're doing a problem, am I exerting the torque with the angular momentum and then I just speed things up or slow things down? Or if I'm exerting it perpendicular, then you would change the axis of rotation. And you get problems like precessing tops and the precessing of the earth and things like that. Those are settings when there's a component perpendicular to the angular momentum. And so with the earth, for example, it's not really speeding up all that much. And it's very slowly spinning down, and that's got to do with the tides from the moon. But and from the sun actually. So, but ignoring that, mostly the Earth's spin is staying the same, but the Earth does precess, so the axis of rotation slowly changes over a period of about 25,000 years, but also from tidal force, tidal perturbations. Okay, so that's torque. Now we have time for an example. Let's do the example. So the example is a string wrapped around a disk. So let's draw the example. So I've got this, bar here, and there's a pivot. There's my pivot. And now, I have more than one color here. We'll use more than one color. So I'll put a disk. So this is a uniform density disk. It has radius r and mass m. And we know the moment of inertia of a uniform density cylinder or disk is 1/2 m. Let's be careful. Yes, mr squared. Squared. I have to make sure I'm using the right notation. And now I have another mass down here, little m, and I'm going to put a string around the disk, and it's connected to the mass. So this is running around the disk. Okay, good. So we know we're expecting, and we have gravity, so mg, this, and then we're going to get a tension on the string. So the mass, all the forces on this little mass, we've got mg and tension, and we add them up, so it's mg minus tension is going to give us mass times acceleration on this little guy. And then, but then the tension is applied here onto the disk. And so if the string doesn't slip, then that's going to exert a torque on the disk, and the disk will now start to spin up. And so the tension will then, we'll get an angular acceleration on the disk that's related to the acceleration of the mass falling because of gravity. So let's be a little bit careful about our coordinates. So I'm going to divide the coordinate system x, y, and z. And so if I put my thumb, index finger, and third finger, I have a right-handed coordinate system here, x, y, z. So this is a right-handed coordinate system, which is good. So just to remind ourselves how to do that. Now let's think about the torque on the disk. So I have R cross F, which is going to be the tension here. Which direction is the torque? So torque is R cross F. So this is in the X direction. This is in the minus Y direction. And X cross Y is Z. So torque is going to be, for us, is going to be R tension minus Z hat. And so it's going to be in that direction. Torque's in this direction. And so remember when we do our right hand roll, we'll put our hand like this in order to get torque in that direction. And that's good because we're expecting the angular acceleration to pull the disk down, right? So alpha dot is going to be less than, or alpha is going to be less than 0 in this coordinate system where we have an angle theta. So this is clockwise. Clockwise is going to give us minus theta, d theta dt. And likewise, we're going to get a negative acceleration so that it makes theta drop here. So that's what we expect based on this, the fact that the torque is negative. Okay, so that's what we're expecting for the angle, for the sines. And my coordinate system, I had y up, but in this coordinate system, the acceleration of the mass A, so let's call, so this is the angular acceleration. Angular accel is alpha. Then we also have a regular acceleration for the little mass m, acceleration, which we'll call it A. And we also expect that to be 0 in the coordinate system with y up. Okay. So what do we know? We know m, g, m, r, what else? I think that's it. And what do we want to find? So we want to find A and alpha and t. Known, unknown. Okay, so these are the things that we're trying to solve. Yeah, okay, so let's write down some conditions. So force, let's do force on this. So the force down is, the force up is T, the force down is mg, and that's going to equal ma, and that should be down. So this gives us T is equal, oops, is that right? No, that's right. Is equal to m, a plus g. That's perfectly fine. Very good. So that's a nice condition. So we already found the torque. The torque was this with a minus sign in front of it. So yeah, so we can use that m a plus g r with a minus sign. So that's our torque. So that's good. And now torque is equal to I alpha. So remember L equals I omega, so torque is I alpha. Here the axis of rotation is this way, the torque is that way. The force is that way, R cross F, but the torque is that way. So it's along the axis of rotation. And so the only thing that's happening is we're going to spin up the disk. So the torque and the angular momentum are in the same direction. So that's good. Okay, so we have alpha, A, and T. We need a third condition. So this is one equation, two equations. We need a third condition. So the third condition is that it's like a roll without slip condition because the string is not allowed to slip on the disk. And so that gives us a relationship between the angular acceleration and the acceleration of this mass. So it's just like the roll without slip condition, and that's equal to this, A over R. So, so if I take this and I replace alpha with this stuff, then I can solve, I have enough conditions now to solve for A and alpha, and if I want to, I can also solve for T. So, so let's do that. Actually, I can solve for, yeah, so let's do that. A is equal to minus G times 2M. Oh yeah, we need to put in this to get rid of I, but there it is. It's 1/2 mr squared. And this is M plus 2M. And there's a minus sign, so it goes down. And alpha is just A over R. So we just take this and divide by R. 2M over M plus 2M. And T is just M times A plus G. So you can just figure out what that is by adding it in here. It actually turns out to be mg times 2m m over m plus 2m. Actually, it's a big M. There. So a little bit of arithmetic, you can solve the problem. So what's interesting actually is the tension, none of these actually, well, so alpha depends on R. But A and T don't actually depend on the radius of the disk. It's kind of surprising, but I'm not sure if that's all that surprising. When we do the roll without slipping, all those roll without slipping problems, the radius winds up kind of dropping out. What doesn't drop out is the factor that's in the moment of inertia. So these 2's here are related to the fact that there's this half in the moment of inertia. So we wind up dividing by mr squared essentially in this problem. Okay, so I think that was all that I had tried to cover on Tuesday when I failed to have a successful recording. But here it is. And I'll post this one on YouTube. So if people want to actually see what I meant to have recorded on Tuesday, here it will be there. Okay, so I'll sign off now.